If your car shakes heavily while waiting at a red light, like a phone vibrating on the gear shift, your vehicle is crying for help. Spending thousands on cleaning the throttle body or changing spark plugs is like giving painkillers to a patient without treating the root cause. Here is a counterintuitive truth. Spending big money on throttle body cleaning and spark plug replacement is basically a placebo that does nothing to solve power loss. Today, let us peel back every layer of this issue. Give me a few minutes and I will break down the engine design principles, the profit logic of repair shops, and the real permanent solution step by step. After watching this episode, you will be the smartest car owner in your social circle, and nobody can trick you. Let us jump straight into the core truth. Why do repair shops always recommend cleaning your throttle body and changing spark plugs? Simply put, these are cash cow projects for them. Think about it. Cleaning the throttle body involves wiping it with a rag and some cleaner. Labor costs are low, but profit margins are 40 to 50%. The best part is that this job requires zero technical skill, so any mechanic can do it. But what about cleaning carbon buildup on the intake valves? That requires removing the intake manifold, locking the crankshaft, and holding your breath so walnut shells do not fall into the cylinder and wreck the engine. It is dirty, exhausting, and risky, yet it pays about the same as cleaning a throttle body. Given this contrast, what would you choose as a shop owner? You pick the easiest path and brush the customer off with a low-cost, high-profit service. This does not necessarily mean mechanics are bad. It shows the survival anxiety of an entire industry facing shrinking competition. With fewer fuel cars coming in and most shops unable to fix electric vehicles, how else can they pay rent and salaries? Speaking of this industry reality, we need to zoom out and look at what is happening across the entire automotive aftermarket in 2026. Industry research reports show that total output value and incoming car volume both dropped by 5% year over year in the first half of the year. Behind these numbers lies the sleepless anxiety of countless shop owners. Fewer cars are coming in, but rent, labor, system maintenance, and customer acquisition costs keep rising. Even more painful is the saying going around the industry that only 5% of stores achieve profit growth, 45% are barely surviving, and the remaining 50% are on the edge of elimination. Against this backdrop, stores rely on high profit and low threshold projects more than ever. Throttle cleaning and spark plug replacement fit these needs perfectly. They are simple, fast, highly accepted by owners, and feature shocking repeat rates. Many shops even follow a fixed script, pushing a basic package of throttle cleaning and spark plug replacement no matter what problem your car has. This combo gets them hundreds of dollars instantly. As for whether your power problem is solved, that depends on luck. I am not trying to scare you. In April of 2026, a car owner complained that a brand dealership in Chengdu forced them to pay for oil channel cleaning and carbon cleaning during a routine service at 38,000 kilometers, claiming the manufacturer required it. The owner later found out the manufacturer never required either item. The essence of this routine trick is taking advantage of the owner's blind spots, using low-cost and ineffective maintenance items to make money while avoiding the core problem that truly needs precise care. Let us do some deeper math. For a throttle body cleaning, material costs are almost negligible. A bottle of carburetor cleaner is cheap, and rags are reusable. As for labor, a skilled worker finishes everything in under 20 minutes. Even counting all costs, materials and labor cost the shop very little. They charge you a lot, so you can calculate the profit margin yourself. Spark plugs are slightly different since the parts cost something, but the markup plus labor still yields huge profits. The key is that the repeat cycle for these two items is extremely short. Many shops suggest cleaning the throttle every 5,000 kilometers or every time you change your oil. What does 5,000 kilometers mean? Many cars have not even reached their oil change interval yet. This frequency completely bypasses normal maintenance needs and exists purely to generate cash flow. So we need to understand what the real culprit behind sluggish power actually is. That culprit is hard carbon buildup on the back of the intake valves, and it is no ordinary sludge. It is engine oil vapor from the crankcase flowing back through the environmental protection system into the intake manifold, then baked, dehydrated, polymerized, and carbonized repeatedly by the hundreds of degrees of heat behind the intake valve, eventually forming a shell as hard and dense as ceramic. Once this thing grows, you cannot scrape it off with your fingernails. Let us break down this process in detail. When an engine runs, the high-pressure air-fuel mixture in the cylinder does not burn 100%. Some blowy gas escapes past the piston rings into the crankcase. This blowbee contains unburned hydrocarbons, water vapor, various acids, and tiny oil droplets. The oil in the crankcase is whipped up at high speeds by the crankshaft, creating heavy oil mist. If released directly into the atmosphere, these harmful gases violate environmental standards. Therefore, manufacturers designed the positive crankcase ventilation system, using intake manifold vacuum to draw these gases back into the intake tract and burn them in the combustion chamber. From an environmental view, this system is a great milestone, but for the lifespan of direct injection engines, it brought a disastrous side effect. Oil vapor is pulled into the intake tract with the blowbee gas and flows past the intake valves. In port injection days, this was not an issue because gasoline sprayed down from above the intake valve, washing the back of the valve with every spray and washing away oil vapor before it could stick. But in direct injection engines, the fuel injectors sit directly inside the cylinder, meaning fuel never touches the back of the intake valves. As a result, oil vapor sticks dryly to the back of the valve and is baked repeatedly by the hundreds of degrees of operating temperature. This baking process has a clear chemical mechanism. Light fractions in the oil vapor evaporate quickly at temperatures between 280 and 350 degrees, leaving behind heavy gummy and asphaltic fractions on the valve surface. These residues undergo continuous dehydration, polymerization, and carbonization under sustained high heat, piling up layer after layer and growing thicker. The resulting carbon layer has incredible hardness and density, far exceeding ordinary dirt and looking more like artificial ceramic material. This explains why ordinary cleaners, fuel additives, and chemical treatments are almost completely useless against it. You cannot reason with a ceramic hard shell using chemical dissolution. The latest engine teardown reports from 2025 show that direct injection cars driven for 30,000 kilometers without any additives can build an average intake valve carbon thickness of 2.3 millimeters. What does 2.3 millimeters mean? Look at a ruler, and you will see this thickness is enough to significantly shrink the cross-sectional area of the intake passage. A research report on passenger car carbon buildup, published by the Society of Automotive Engineers in 2023, also noted that direct injection engines with mileage exceeding 40,000 kilometers have average intake valve and combustion chamber carbon thicknesses between 1.2 and 2.1 millimeters, with severely affected cars even having their injector holes blocked. This brings us to the first counterintuitive misconception. Many people think this is caused by poor fuel quality, but let me tell you, in North America and Europe, direct injection BMW owners using top-tier global gasolines still have to get Walnut shell cleaning after 50 or 60,000 miles. Why? Because gasoline simply cannot spray onto the back of the intake valves. You drive a direct injection car where the fuel injector sits inside the cylinder. No matter how powerful the polyethylamine components are in your fuel additive, they travel through the fuel lines and can never reach the airflow path behind the intake valves. Let us talk completely about fuel additives. Polyethylamine, or PEA, achieves amazing carbon removal rates under ideal laboratory conditions, sometimes reaching 98%. In the spring tests of 2026, clean type additives under National 6B standards reached a carbon removal rate of 92% in labs, with fuel atomization improved by 23%. These data points are real, and I have seen the reports. But where is the catch? The catch lies in the gap between laboratory conditions and real-world driving environments. Lab tests mix additives in precise fuel ratios on a calibrated test bench engine where all temperatures, pressures, and injection pulse widths are optimized. More importantly, many lab tests focus on combustion chamber and injector carbon, areas that fuel actually reaches. But when you put that additive into your car, it faces the hard carbon on the back of the intake valves. Fuel additives start in the fuel tank, get pressurized by pumps, atomized by injectors, and sprayed straight into the cylinder. Their delivery path has zero to do with the back of the intake valves. I saw a real-world test shared by a car owner that proves this point. He added 5 bottles of fuel additive to his 60,000 kilometer car, and while combustion chamber carbon was partly cleaned, the hard shell on the back of the intake valves remained completely untouched. Only after getting walnut shell cleaning did he recover 85% of his intake efficiency. So stop believing that fuel additives can cure intake valve carbon. They only clean injectors and piston tops, serving as a preventative measure. For carbon already baked into a hard shell, adding a tank of fuel additive gives you no more than psychological comfort. Speaking of driving fast on the highway, We need to debunk that myth too. Many veteran drivers believe that a high-speed highway run blows carbon away. The longevity and widespread reach of this myth almost match the urban legend that engine oil must be changed every 5,000 kilometers. From a fluid mechanics perspective, this claim does not hold up. When engine speed rises, airflow speed in the intake tract indeed increases, but right at the back of the intake valve, a natural boundary layer resistance exists. What does this mean? The layer of air hugging the metal surface of the valve has an almost zero flow speed. High-speed airflow never touches the very bottom of the carbon layer. Even if airflow could reach it, the shear force generated by high-speed air would only affect the loose dust on the very top layer. For ceramic like carbon formed by thousands of hours of high-temperature polymerization, its chemical bond with the metal valve body is extremely strong, and simple airflow brushing cannot break this bond. Blindly pushing high engine RPM long-term will not blow away carbon. Instead, it increases engine wear and worsens fuel consumption, making it a losing trade. Now let us talk about the most powerful permanent solution, which is walnut shell physical injection cleaning. The principle is very similar to jewelry polishing. Crushed walnut shell particles are blasted in with high-pressure gas to knock the carbon right off. This technology has existed for decades, originally adapted from polymer surface treatment processes in the aerospace industry. Certain precision aerospace parts required removing surface attachments without damaging the substrate, and engineers found walnut shell particles to be a natural and perfect medium. Later, this technology trickled down into automotive repair, evolving through multiple generations to reach the fifth generation by 2026. Compared to early equipment, fifth-generation machines represent a qualitative leap. Early walnut shell equipment consisted of a compressed air tank and a nozzle where pressure control relied entirely on the mechanic's feel, with spray location and duration based purely on experience. Back then, a walnut shell cleaning was 30% skill and 70% luck. If you met a skilled master, results were instant. If you met a sloppy worker, you prayed for the best. But new generation equipment is completely different. A closed-loop negative pressure recovery system simultaneously vacuums up walnut shell powder and carbon debris after impact, leaving no residue in the intake tract. A 360-degree rotating nozzle covers every corner of the back of the intake valve, leaving zero cleaning dead zones. A constant pressure control system ensures every blast has precise and controllable force, preventing uneven cleaning or damage to the valve seats due to pressure fluctuations. Why are walnut shells so amazing? From a material science view, their Mohs hardness is between 2.5 and 3, carbon hardness is between 3 and 4, and the aluminum alloy cylinder block and valve substrate have a hardness above 6. This hardness gradient is too perfect, as walnut shells sit right between carbon and aluminum alloy. When walnut grit is blasted onto the carbon surface at 4 to 6 atmospheres of pressure, the impact energy creates micro cracks in the carbon layer, followed by crack expansion and interface peeling, causing the whole chunk of carbon to fall off the valve surface. Because walnut shell particles contain wood fiber structures, they deform or fracture upon impact, absorbing all remaining kinetic energy so that by the time they reach the metal surface, the force has decayed into a safe range. Take a BMW B48 engine with 80,000 kilometers. After removing the intake manifold and looking through an endoscope, the carbon layer on the back of the intake valve is as thick as a winter coat, measuring 2 to 3 millimeters. This thickness is enough to cause valve leakage, severe idle instability, and sluggish acceleration even with the pedal floored. After 30 minutes of walnut shell cleaning and another endoscope check, carbon removal exceeds 95%, exposing the shiny metal body underneath. The owner reported a throttle response recovery of over 95%, delivering a silky smooth feel as if the engine had been replaced. However, here comes the most crucial and dangerous part. At least 3 out of 10 mechanics will try to skip the step of manually turning and locking the crankshaft. Why must you turn the crankshaft? Because during walnut shell blasting, high-pressure gas and particles shoot toward the back of the intake valve, and fine particles inevitably slip past valve gaps. If an intake valve is open, these particles fall straight into the cylinder. No matter how soft walnut shell particles are, they are still solid particles. The oil film between high-speed piston rings and cylinder walls cannot stop them, leading directly to scratches or severe scoring. Therefore, standard operating procedure requires using a manual wrench to turn the crankshaft, adjust the intake valve of the cylinder being cleaned to a fully closed position, and lock the camshaft with a special tool to ensure the valve does not accidentally open during cleaning. Only after completing this step can blasting begin. This step is tedious and tiring, but absolutely necessary. Unfortunately, some shops skip it to save time or out of ignorance. Once sand enters the cylinder, thousands of dollars in repair costs go down the drain, and the engine is completely ruined. Would you rather spend a bit more money at a large shop with strict procedures, or gamble at a roadside stall for a cheap price? Share your choice in the comments. Thanks to the natural organic nature of walnut shells, even if tiny amounts of fine powder accidentally remain in the combustion chamber, the 1,000-degree temperature during engine ignition burns them completely into harmless ash, leaving zero residue, zero corrosion, and zero safety risks. This is much better than chemical cleaning methods, where any chemical residue left in the intake tract can react with engine oil and form new gummy substances that clog other lines. With technology popularization and falling equipment costs, walnut shell cleaning prices in Tier 1 domestic cities reach transparency by 2026. Single service costs range from 800 to 1,500 yuan, depending on the vehicle model, taking about 1.5 to 2 hours. This is much lower than prices from a few years ago. An increasing number of official brand dealerships and high-end maintenance stores are adopting 5th-generation walnut shell cleaning equipment in bulk, moving this high-end precision maintenance technology from tuning circles into the mainstream maintenance market. Since walnut shell cleaning works so well, we return to a soul-searching question. Why do manufacturers not kill this root cause directly at the design stage? To answer this, we must trace the evolution of fuel injection technology. In traditional port injection days, fuel injectors sat on the intake manifold, where fuel and air pre-mixed before entering the cylinder through the intake valve. The genius of this design was that every time fuel was sprayed, gasoline washed over the back of the intake valve from above, dissolving and carrying away freshly attached oil vapor and gum. This created a natural self-cleaning cycle. Many old port injection cars from 10 years ago still have gleaming metal color on the back of their intake valves after 100,000 kilometers. This was the structural dividend of port injection. Later, emission regulations grew stricter and combustion efficiency demands rose, making port injection hard to maintain. Direct injection advantages were too obvious, as injection pressure surged from tens of bars to 200 or even 500 bars, atomizing fuel into micron-sized particles for more uniform mixing, fuller combustion, better knock control, quicker throttle response, and lower fuel consumption. Overall combustion efficiency improved by about 20% compared to port injection. These were hard metrics automakers could not refuse, but the price was the loss of intake valve self-cleaning capability, which combined with continuous oil vapor from the PCV system made carbon buildup a byproduct of technological progress. This trade-off is common in engineering, trading reliability for massive performance gains. Direct injection engine test bench data looked great, fuel consumption numbers looked low, and tailpipe emissions were clean enough. Whether your intake valves built up carbon after 40,000 kilometers became the aftermarket department's problem. Could we solve carbon buildup while keeping direct injection advantages? Absolutely, and the answer is a dual injection system. Low speed and light load conditions use port injection to wash the valve back clean, while high speed and heavy load conditions switch to direct injection to ensure power output and fuel economy. The car computer calculates the optimal injection strategy in real time based on engine speed, load, water temperature, and intake temperature, making switching completely imperceptible. Toyota's D4S dual injection system was among the first mass-produced, using port injection during cold starts and light loads to reduce carbon, and switching to direct injection under heavy loads. Volkswagen's 5th-generation EA888 engine upgraded to a dual fuel injection system, combining port injection with direct injection and boosting pressure to 500 bars. Volkswagen owners reported that newer cars with dual injection had far less throttle carbon after 5 years than older EA888 models. Toyota went further, raising injection pressure from 20 megapascals to 35 megapascals to achieve ultimate fuel atomization and lower soot emissions. Real-world vehicle testing, verified by 2026, showed that new dual injection engines extended heavy carbon accumulation cycles from 40,000 kilometers for pure direct injection to over 120,000 kilometers, largely solving a stubborn industry headache lasting over a decade. The downside is system complexity and higher costs, requiring high and low pressure pumps, dual injectors, and finer ECU calibration. Yet the reality is that tens of millions of older pure direct injection cars in the existing fleet have been strategically abandoned by automakers. Did automakers not know that installing an oil catch can could intercept 90% of oil vapor at the source? Of course they knew. In mature automotive markets like North America, Australia, and Europe, oil catch cans became the very first modification new direct injection owners installed after registration. Installing a catch can right from day one cuts off the intake valve carbon problem at the root. Third generation oil catch cans are in an entirely different league compared to early crude versions. Early products were just a tube connected to an empty container where oil vapor cooled into liquid drops at the bottom, offering low efficiency and frequently freezing and clogging in winter. Third generation products feature labyrinth-style multi-layer condensation baffles combined with cyclone centrifugal separation structures. Incoming oil vapor is thrown against container walls by centrifugal force, passes through multiple baffles for collision and condensation, and leaves only pure gas to return to the intake tract for combustion. Official tests show oil and gas interception efficiency exceeding 90%. If it works so well, why do manufacturers not make it standard equipment? Let us do the math. That small container requires manual opening of the bottom drain valve every 5,000 to 10,000 kilometers to clear accumulated black liquid waste oil. Skipping it once might be fine, but ignoring it for 10,000 kilometers means the catch can fills up and waste oil overflows. If you suddenly floor the accelerator on the highway, the massive vacuum in the intake manifold sucks the entire full can of waste oil straight into the intake tract. A huge surge of oil floods the combustion chamber, making the air-fuel mixture extremely rich, causing severe engine knocking, misfires, and runaway RPM. In severe cases, connecting rods bend or break, punching through the engine block, and instantly destroying the engine beyond repair. Ask yourself honestly, over half of car owners never open their front hoods from purchase to sale. This is no exaggeration. 2026 third-generation automotive research statistics confirm this number. When people do not even know where the dipstick is, expecting them to crawl under the car every 5,000 kilometers to drain waste oil is a pipe dream. If automakers made oil catch cans standard equipment and a wave of engines failed due to maintenance negligence, who takes the blame? Owners would blame product quality and demand a new engine, while automakers would claim it was a maintenance part requiring timely service. Where is the proof? Who proves owners failed to drain the waste oil? Owners could argue the manufacturer never warned them. Was it in the manual? Yes, but most owners never read the manual. Such endless legal disputes lead to massive lawsuits and brand disaster. After calculating risks costs exceeding rewards, legal and quality departments reach a simple conclusion: do not install it. This is an inescapable responsibility trap. Therefore, automakers prefer letting you pay for walnut shell, cleaning every tens of thousands of kilometers, rather than planting a recall time bomb. Speaking of this, let us address a question many car enthusiasts care about. Do different engine models differ in carbon severity? To be honest, the differences are quite significant. Although all direct injection engines face the destiny of intake valve carbon, stack-up speed and severity vary noticeably across brands and models. This relates to engine design orientation, PCV system structure, oil separator efficiency, and valve lift or timing calibrations. Take BMW's N-series engines as a classic example of heavy carbon accumulators. Older direct injection models like the N20 and N55 could build enough intake valve carbon by 40,000 kilometers to make you doubt life. Opening the intake manifold revealed a thick, hard black shell on the valve back resembling armor. Later B48 engines improved structural optimization and oil separators, but carbon problems persisted, though slightly better than the N series. Volkswagen's EA888 series is another heavy carbon disaster area. With enormous domestic market presence from the first generation to the fourth generation Evo, carbon problems span its entire life cycle. Many EA888 owners experience cold start shaking, unstable idling, and sluggish acceleration around 50 to 60,000 kilometers. The fix is uniform. Remove the intake manifold and perform walnut shell cleaning. Once done, the world becomes peaceful again, but after another 40 to 50,000 kilometers, fate returns. Japanese direct injection engines tend to accumulate carbon a bit more mildly. Honda's L15B Earth Dreams engine, for example, has carbon issues, but accumulation thickness at equal mileage is usually thinner than German counterparts. This may relate to Honda's PCV system design and oil separation efficiency, or conservative operating temperature settings. Lower operating temperatures slow down oil vapor oxidation and carbonization, leading to slower carbon formation. Note that I said slower, not absent. Honda direct injection engines still develop intake valve carbon. They just reach the critical threshold 1 or 20,000 kilometers later than German engines. Failing to clean at 60,000 kilometers still brings shaking and sluggishness, treating all direct injection owners equally. Another easily overlooked factor is how different engine oils affect carbon formation speed. Many owners have no concept of this, thinking oil is just for lubrication and has nothing to do with carbon. It has everything to do with it. Engine oil contains 10 to 20% volatile fractions, and volatility varies greatly across brands and grades. Low flash point and high volatility oils evaporate more vapor under high crankcase temperatures, which gets drawn into the intake tract by the PCV system to become direct raw material for carbon. Conversely, choosing high flash point, low volatility fully synthetic oils significantly reduces oil vapor generation, delaying carbon formation at the source. Most owners ignore this detail, yet it offers the lowest cost and most realistic results. Spending a bit extra on quality low volatility oil when changing oil prevents intake valve carbon better than 10 bottles of fuel additive. Of course, do not expect oil changes alone to completely solve carbon. They only delay, not eradicate. So how should ordinary car owners face this structural destiny? My attitude is clear: do not panic, but do not be lazy. Once you understand this issue thoroughly, you realize intake valve carbon in direct injection engines is no mystery, but a routine structural problem overpackaged by the industry and misunderstood by owners. Its causes are clear, its mechanics defined, and its prevention and treatment methods mature. Your primary task is avoiding distraction from miscellaneous ineffective projects. Let us break down strategies by mileage stage clearly. From a new car up to 40,000 kilometers, do nothing special. Maintain normal oil and filter changes, replace air filters as recommended, and avoid value-added services like engine flushes, fuel line cleanings, or intake tract cleanings. At this stage, any carbon present is just a thin layer with minimal performance impact. Endoscope inspection might reveal gray or brown deposits, but nowhere near enough to restrict airflow. Why wash it? Removing the intake manifold, strains, gaskets, and joints. Do not disassemble without reason. Your only task at this stage is choosing quality oil during changes, as low volatility, fully synthetic oil keep our carbon generation rates at a minimum. During the 40 to 60,000 kilometer stage, start paying attention to your car's condition. Does cold start shake a few seconds longer than before? Does the idle tachometer needle drift gently? Is throttle response duller during stop and go city driving? Does acceleration lack that previous pushback feeling? These are signals of declining intake efficiency. The most rational move is visiting a professional repair shop with an endoscope for an intake tract inspection. An endoscope inserted through the manifold joint clearly reveals the true state of the intake valve back. Whether it is light deposition or hard sintering, thickness levels, and valve closure impacts become instantly visible. If light carbon is found, observe further without immediate treatment while optimizing engine oil selection. If inspection reveals a hard sintered layer, excessive thickness, or abnormal power behavior, do not hesitate to get a direct walnut shell physical cleaning. Avoid fancy tricks like chemical liquid drips or dry ice cleaning. Chemical drips use solvents that fail to clean thoroughly and can drop large chunks of carbon onto valve seats, causing valve leaks. Dry ice cleaning operates at too low temperatures and risks thermal stress on metal parts. Walnut shell blasting is universally recognized as the single golden standard in global auto repair, with no exceptions. After walnut shell cleaning, consider a long-term investment, installing a high-quality third-generation oil catch can, but realize that installing this adds regular maintenance responsibility. Check the oil level every 5,000 kilometers and drain waste oil without being lazy. If you keep it up, this investment pays off by drastically slowing carbon growth, extending the next walnut shell cleaning interval from 40,000 to 80 or 100,000 kilometers. If you lack patience and memory, stick to traditional walnut shell cleaning every 40 to 60,000 kilometers. As for shops pushing fuel additives every 5,000 kilometers or throttle cleaning every 10,000, throw the quote back on their desk and walk away. Remember 3 things. First, fuel additives cannot reach intake valves, so stop blaming them. Their cleaning action stays restricted to combustion chambers and injectors, contributing 0 to intake valve carbon. Second, cleaning the throttle every 5,000 kilometers is pure overmaintent, a shop survival baseline rather than your necessity. Throttles only affect idle stability when dirty, and most modern direct injection electronic throttles self clean far better than you think, needing no manual touch before 60 to 80,000 kilometers. Third, the 40 to 60,000 kilometer window is critical. Inspect with an endoscope when noticing anomalies and use professional walnut shell cleaning for hard carbon. Do not wait until carbon causes valve leaks and hard cold starts when combustion chamber carbon also becomes severe, making repairs more costly and complex. This episode is packed with solid facts worth saving. Check it before your next repair visit so nobody takes advantage of you. I am your truth telling deep explainer waiting in the comments. How many kilometers has your car driven? What brand of direct injection engine does it have? Did you experience shaking or power loss? How much does walnut shell cleaning cost locally? Share to help fellow drivers avoid repair shop traps, and see you next time.